This video will cover section 3.11, related rates, and this is the second part of the video. So one thing that I forgot to show you when we were discussing and solving problems, example 1 and example 2, I forgot to show you the awesome interactives that come with our textbook. So that's what I want to do just to make a little bit more sense of our problems. And remember, the first one was about the oil spill. And we discussed that as the radius was changing, so was the area of the area affected, the spill, affected by the spill. So let me show you here on the textbook, on our ebook actually. And so that is how they have the image at the end. So I'm going to have to reset it. And so I'm going to push play. And so you can see that as the radius increases, so is the area, and so is the affected total area by the spill. And so it is no surprise that the damage will be exponential. Okay, now let's go ahead and look at number 2. And remember, we got a negative result, I believe. Yes, negative 192 right here. And so I explained something about how the plane was, the planes were getting closer to each other because they were getting closer to the airport. And so this is how it will look once both airplanes are about to land at the airport. So I'm going to reset the image. And so this is how we start at when we start taking the data. So that's how the planes fly, and as one moves north here, and the other one moves west here, they both get closer to each other. They're getting closer to the airport and getting closer to each other. I'm going to play it again. Now I want you to focus on this graph here, and you can see how the distance is decreasing, and so that's why our solution at the end is negative. So the distance between the two planes, it is decreasing. Okay, so now our next problem, let's go ahead and read it here. So we have some sand is falling from an overhead bin. And so here you have the image. So here is the overhead bin. The sand is falling from there, and it is accumulating in a conical pile. So it looks like a cone. And with the radius, that is always 3 times its height. So I assume that's going to be important in a minute. If the sand falls from the bin at a rate of 120 cubic feet per minute, remember we're talking about volume, so that's why we have cubic feet. How fast is the height of the sand pile changing when the pile is 10 feet high? And so let's just see quickly how the interactive looks. That is when the sand has already, most of it has fallen, actually. So I'm going to reset it so you see how it looks at the beginning. Okay. So let's try it there. So we reset. And so this is when the sand has not fallen or starting to. So if you notice here, the black line is representing the height of the cone, okay? And so right here, the height is a little bit above 0. I'm going to estimate a 2, for example. And the graph that is represented in red is, that is colored red, is representing the radius, how fast the radius is changing of the cone. And what we have here on the right side is how the volume is changing. And so the volume of the pile of dirt is increasing. So you can see that increasing here. Also, the height is increasing and the radius is increasing. But if you notice, the radius is increasing at a faster rate than the height. So let's play it. Okay. here we go a little bit out of bounds, but you can see, you can infer that the pile is also increasing on this area. So I'm going to reset and play it again. So try to follow the height and the radius this time, and see how they are increasing. The radius increases faster. And then look at how the volume is also increasing, the volume of the pile of dirt. So now let's go back to the problem. And we're talking about example 3. So we start with the formula for the area of a cone, and we have here. So the volume of a cone is given by 1/3 times pi times r squared times the height. And let's do a quantitative analysis. So we have something that is telling us that the radius is going to be always 3 times the height. So what we're going to do there is we're going to replace, we should be replacing the radius with this quantity right here, 3 times the height. So I'm going to do that. So 1/3 times pi, instead of radius, I'm going to have 3h, and then square, remember, we're replacing that for the radius, and then times h. Now we're going to simplify the formula a little bit more, and so this will be 1/3 times pi. Remember here we have to square the 3, so that will give me 9, and then we square the height, so that will be height squared. And then here we have the height to the power 1. So finally this will be 1/3. In fact, it will be 9/3. Oops, this is not like that. So it will be 9/3 pi. And then here we add the exponent, so that will be h to the power 3. And of course, if we simplify this fraction, 9/3 will be 3. And so we changed our formula from here to here only because we knew that the radius was always going to be 3 times as large as the height. And that's it. Now let's see what else we were given. And we were given this very important piece of information. How fast the volume is changing per minute. So they're actually giving us dV times dt. So how fast the volume changes with respect to time, and that is actually 120 feet to the power divided by minutes, because those are our units. Now, what we're going to do is take the derivative here, and so right here we will have dV over dt. Here we're going to derive, so we're going to use power rule, so we will have 3 times 3, that will be 9 pi h to the power 2. And so in this case, we're deriving h, so it will be how fast is the height changing with respect to time. And so we go back to the problem, and now I'm going to read the question again. And it says, how fast is the height changing, the height of the sand pile changing when the pile is 10 feet high? So we want to know what is dH over dt, that is the question, when the height is equal to 10 feet. So remember, the height is not constant, however, here we're making it, we're taking just one set value. And what we're going to be looking for is this quantity here. Now, let's see what do we have to substitute. So we can substitute this one with that, 120 cubic feet per minute. And we could also substitute the height with 10 feet. So we're going to do that. So this will be 120 cubic feet per minute. Here we will have 9 times pi, and we have 10 squared, and we are going to be solving for dH dt. Okay, so let's see what we can do. So 120 cubic feet per minute. And here I'm going to multiply this quantity. So 10 squared is 100. 100 times 9 will be 900. So 900 pi dH over dt. Now remember, the question is asking us how fast is the height changing when the height is 10. So we're going to be solving for dH dt. And remember that the 900 pi is multiplying to it. So it will be enough to just take the 120 cubic feet divided by minutes here and divide that 900 pi. And so I'm going to get the answer. And so that will give us approximately 0.042 feet per minute. And so you might be wondering how that happened. Well, remember that the units from here, we had something, if we look at the first formula, we had the radius. Remember, the volume is calculated by the radius. I'm sorry, 1/3 pi times the radius times the height. And so if you think about it, from the radius we're getting feet, and from the height we're also getting feet. So we actually forgot that the units that were here were feet squared. Why squared? Because the radius was given in feet, and so was the height given in feet. And so that's why we have feet squared here. And so that will cancel with the cubic, and that's why our units will be that. It also makes sense because we're talking about how fast the height is changing with respect to time. And so it makes sense that it will be a linear unit divided by time. And so that is what we get. So let's move on to the next and last problem of the section. So we have an observer stands 200 meters from the launch site of a hot air balloon. The balloon rises vertically at a constant rate of 4 meters per second. So that's going to be important at some point. How fast is the angle of elevation of the balloon increasing? 30 seconds after the launch. Now the angle of elevation is the angle between the ground, so here's the ground, and here is the observer. So the angle of elevation will be right here. And so that angle, we're going to call it theta, is changing with respect to time. So here the independent variable is time. Okay, now we also have something such as the vertical distance, and so this is y of t. And we have something such as the horizontal distance, so let's just call it x of t. Now, for this, since we have a right triangle, we have an angle of elevation, and we have one side, and we don't have the other, but we could find it. We're going to be using a trigonometric ratio. And we're talking about, well, let's see, how fast is the angle of elevation of the balloon increasing 30 seconds after the launch? So let's see, we also know that the observer is 200 meters from the launch site. And so what trigonometric ratio can we use that will include something that is coming from here? Why from here? Well, because we have one of the rates for how the balloon is rising up vertically. And so that includes the adjacent side because we have it here, adjacent, and it also includes the opposite side to that angle. So think about it, opposite over adjacent, so that will be tangent. So the tangent of theta will be given by the opposite side over the adjacent. Okay, now we already know that this is a function of time. And so let's solve for theta. Okay, so before we solve for theta and get into something more complicated with taking the derivative of tangent inverse, we're just going to take the derivative of tangent. But before that, let's go ahead and replace the opposite and the adjacent with actual variables or numbers. And so the opposite, we are just going to call it y for now, for vertical distance. And our adjacent is going to be given the number of 200 meters. Okay, now we're going to take the derivative here, and we all know the derivative of tangent is going to be secant squared of theta. And we are deriving theta with respect to time, so we need the notation d theta over dt. Now for the right side, what I'm going to say is 1 over 200. So this quantity here, let me change it first. So y over 200 meters is the same as 1 over 200 times y and then meters. And so this is to the power 1. So if I want to take the derivative, it will be 1 times this fraction, and then y to the power 1 minus 1 is 0. Or in other words, it would just be the number 1 over 200. And for the units, it will be dy, or I'm sorry, not the units, but since we're deriving y with respect to time, dy over dt. Okay, so now going back to the problem, and it does say that the balloon is going up at a constant rate of 4 meters per second. So that 4 meters per second is saying the balloon is going up, so that this is what they're giving us, dy dt. So dy dt is actually 4 meters per second from here, vertically. So we're going to be replacing that with 4 meters per second, and but before we do that, let's go ahead and solve for, we're going to be solving for d theta over dt, the one here, because that is what the question is asking us. The question is saying how fast is the angle of elevation, right here, of the balloon increasing. So that's going to tell us, that's telling us it will be positive 30 seconds after the launch. So let's go ahead and solve for d theta over dt, and that will be, the secant square is actually multiplying d theta over dt, so I'm just going to take it across to the other side. And so here I'm just going to have dy over dt. We have the 1 here, we have a 200 here, and we're going to take the secant square, and it's going to be dividing here. So let's see what we get from here, and that's going to be d theta over dt is equal to 1 over 200 secant square theta. I should have just left dy dt here. Okay. Now what I'm going to do here is use reciprocal identities. So secant square, it will be the same as cosine square. I'm sorry, 1 over secant squared is the same as cosine squared. And we still have the 200 here. dy dt, d theta over dt. Okay, so now we're going to be creative in how we use the information about how fast the balloon is going up and the 30 seconds. Because if you look at our algebra, there's nowhere to substitute t with 30 seconds. So what we're going to have to do is somehow substitute that for the dy dt. But we need to figure out something to do with the 30 seconds. And so what I need, actually, let's think about this. So what do you need to find the cosine of an angle? And so to find the cosine of an angle, you need the adjacent side, but you also need the hypotenuse. And so let's see, what do we have so far? So we know that this balloon is going at a constant rate up of 4 meters per second. And we're talking about 3 seconds. So in 3 seconds, how far did the balloon travel? So here it was 4 meters, 4 meters, and 4 meters. So in total, the balloon, after 3 seconds, it traveled 4 times 3, so 12 meters. It doesn't make sense. Oh. Okay, so the balloon is not traveling for 3 seconds, it's actually traveling for 30 seconds. So if it travels for 30 seconds, it's going 120 meters. So sorry about that. So that makes more sense because the horizontal distance is 200 and then the vertical distance is 120. And so how are we going to get the hypotenuse? Why do we need the hypotenuse again? Because we're talking about cosine right here. And so the hypotenuse, of course, it will be pretty simple. That's going to be given by the square root of 200 squared plus 120 squared. And so what we will get for that side, we just put that on the calculator. Approximately, it will be 248 meters. And so that is what we are getting after 30 seconds. And how do we get that? Remember, this is traveling 4 meters per second. So 30 seconds, 120 meters. That's how we found that. That was given to us. And so now that we know the adjacent side, and remember cosine, again, we're going to need adjacent, and we need the hypotenuse. We do have the adjacent here, and now we do have the hypotenuse. But to find the hypotenuse, we have to find the opposite side as well. So this should be just a matter of substituting. So we're going to end up substituting here. So for dt is going to be the cosine square. So we have the adjacent side being 200, and then the hypotenuse, that was the 233 point something, 248. But remember, we have to square it. Okay, and then we have 200 here on the bottom, and then for dy dt, we're going to substitute that with the constant rate of elevation, which was 4 meters per second. And so 200 is also in meters. And so let's see what we're going to get. And so what we get at the end is going to be 0.0147 radians per second. Of course, if you do have your calculator set to degrees, then you will see that in degrees. But it is less than 1 degree, just so you know. Now let's just see the animation quickly before we stop the video, stop recording. So if we go here, that was the one for the pile of dirt. And so here is the balloon. And here's the image of how the triangle looks, right, after the balloon has reached that point right there. But let's see how it will look. So I'm going to reset it. Now the balloon is here on the ground. And so we're going to play. The balloon is going to be going up, up, up. And you're going to see this angle here is going to be going from 0 to increasing. It's going to be opening up. And so on this graph, you can see the angle going from 0, the angle of elevation, going up in that way. And so as the height increases, the angle of elevation also increases. And you can see it on both graphs. I know that this problem might not make a lot of sense to you, but I promise maybe if you watch the video again, at least this last problem, it will make a little more sense. So this is the end of the video.